Welcome to our Waterfall tutorials. In this set of tutorials, I'll share the process and techniques of this waterfall creation. The project I show you is at 60 FPS, which is my usual setting in the previous projects. Actually, I've tested the effect at 30 FPS and found that the water dynamics at different FPS are different. So FPS affects the water dynamics, but it's not the main point here. Well, in this set of tutorials, I will talk about the principal factors affecting the dynamics of the waterfall and analyze the characteristics of the waterfall based on the real reference. Also, I will show you how to manually convert particles to mesh and explain some detailed settings of the Whitewater. Finally, I will share the material, rendering, and compositing. All of these are the practical experience and techniques I accumulated from my work. Hope it will be helpful to you. Alright, let's get started in the next video. Before we start creating a waterfall, we need to find some references. In fact, no matter what we make, references are always essential. They're pretty helpful for us to set a clear goal. Then we need to analyze the characteristics of the reference. I want to make this kind of waterfall. Let's first analyze the characteristics. On the surface of the upstream water, there is some stacked foam in some areas because of collision or rugged terrain, while in some areas there is less foam because the terrain is relatively flat. And also here, the water dynamics at the bevel is quite different. We can see different surfaces of terrain generate different water dynamics. Briefly speaking, the terrain has a great impact on water dynamics. This is a pretty important point. When I created the waterfall at first, I made the terrain uneven in order to get more foam, like here in the reference. I simulated flip based on this terrain before. After testing, I got this effect. Compared with the reference, this is not what I want, because the surface of the falling water is smooth in the reference without too much disturbance. Also, I didn't add too much noise, but the effect after simulation is a bit chaotic, far different from the dynamics I want. Later, I found the surface of the terrain should be relatively flat actually, but I referred to the surface here to sim the waterfall. Here is uneven, which results in unstable water dynamics. So the issue was caused by the terrain. Then I revised it and got the second version. There are two versions in the project. Except for the terrain and parameters, the general workflow is the same. Here I will show you the final version and skip the previous one. This is the modified terrain. Compared with the previous version, it's much flatter. I modified the bevel and the relief of the terrain according to the reference. We can see the water dynamics is pretty close to the reference. So the relief of the terrain has a great influence on the dynamics of flip. Sometimes the simulated dynamics is not good, mainly due to the terrain. Look at this picture. This is the simulated water dynamics. The water rolls back greatly. It's out of the normal proportion with the man, which is potentially because of the terrain. In the projects of making flat water, the influence of terrain on water dynamics may be up to 60%. The noises and force fields in depth may make up 40%. When we make flat water, if the flip dynamics is not good, neither too much noise nor force fields are added, then you can check whether the terrain is proper. Sometimes a slightly concave terrain would make the flip dynamics look bad. So the terrain is pretty critical. Let's look at the workflow of the terrain. Since these two versions are the same except for the parameters, let's take a look at the modified terrain. Here on the right is the final version. Let me introduce it briefly. These nodes are to set the terrain and simulate flip. This is the process of simulating Whitewater. These are for final rendering. This is the terrain made by height field system. It started from a plane, then I added a resample to raise the subdivision. A mask was drawn here because I wanted to add a noise only to this area. Then I raised the subdivision again. Next, I made the terrain a bit stepped according to the reference. So I made it like this. Next, I selected the part in the back, weighted, and raised it. Then there was a shear drop. Next, we got the mask of the drop area by the layer calculation. Different mode was applied for this mask and the other one. This way, we got the mask of the drop area. I added noise to this area and then blurred the terrain a bit, which can add rectangle-shaped texture to the terrain. Next, I distorted the bevel of the terrain, since in the reference the bevel of the terrain lacks some changes. To make the simulated water have more layers, I modified this area. Then I drew a mask in the back with a pretty large blur radius and then expanded it a bit. Then I lifted the terrain a bit and made it slightly sloped according to the real terrain. Next, I removed the mask. This is the final terrain without much up and down. It's relatively flat overall. Then I converted it to mesh and then added a poly reduce to reduce polygons. Then cast it. If there's only terrain, it is too flat, so I added a few rocks. Here is the network of making rocks. It was a sphere. We subdivided it and added a mountain node. Here I added some noise to make it like a rock. Then I duplicated it several times and placed them beside the terrain. Here I deleted the lowland of the terrain because we don't want the water to collide with it, but just fall directly. Then I extruded it to get a volume and merged it with the rocks. This is the final terrain. The notes below are to set collisions in Flip. That's all for this video. See you soon. In the previous video, we mainly talked about the terrain. In the following episodes, I will remake the waterfall step by step. It'll definitely be helpful to your production. Here are the two main goals from this video. One is the creation of flip source and the initial state of water. The other is the workflow of simulating and caching flip. Besides, I'll share some tips on caching. Now let's begin. Okay, let's jump over to Houdini. Here are the nodes of the final terrain. These two are for rendering. This part is to sim the collision object of flip. Delete it first. Later we will remake it. We mentioned in the previous video that the lowlands was deleted to avoid collision with water. We deleted non-selected and cleaned unused attributes, then extruded this part to get the volume. It will be used as the area of killing particles. So will these two boxes. I'll explain it in detail when we simulate flip later. Then here, this node is to extrude the terrain down. This one is to move it up a little. So it's like the terrain has been extruded up on the basis of the original version, because the depth here is linked to the translate here. Here we created the initial state. Come to the object network. Delete these nodes first. We will remake them later. Firstly, let's import the initial state into a new geometry. I'm personally used to creating a box before the simulation as the scope of the flip. Let's take a look in the top view. Try to fit it to the four sides of the terrain. Raise it slightly. Okay, this box will be the range of the flip. I prefer to use a box to control the boundaries of flip, which is convenient. And when we create a flip source and the initial state, it's also a necessity as I'll make a procedural control. I want the source and the initial state like this. I'm gonna put the source here and the initial state here. They're right next to each other. So when I adjust the source widths, the width of the initial state will also be changed. Here, I'll need a box to achieve this kind of procedural control. Okay, let's create a source at the edge of the terrain. Move this side leftward a little to leave a space for the source. Then we make a Boolean operation between the initial state and the scope of the source. Hide this geometry. Select Intersect. Now we can see the source is cut off. Duplicate Boolean node. Alter the operation to subtract. Here we can see the actual area out of the box. Since the initial state should be within the range of the flip, we don't need the extra area. Therefore, we also need a Boolean operation between the initial state and the box 1. Now this extra area is deleted. Then wire up the Boolean 3. In this way, we get the source area. Besides, we only need the initial state on the uplands of the terrain and do not need it on the lowlands. Connect another bound after bound 1. We can adjust this bound to exclude the lowlands. Alter this value. Put the display flag on Boolean 3 first. Now the adjustment gets easier, roughly like this. Then let's check the Boolean result. Alright, we've gotten the initial state I want. Here is a thing that we need to note. The rocks here cross the water. The intersecting part of the initial state needs to be cut off. Copy the path of this rock. We import it into this geometry. Hold down the Alt key to duplicate this node. Paste the path of this rock. Hide other objects. This is the rock. We need to remove the intersecting part from the initial state. Here we do not use Boolean because these rocks are intersecting. If using Boolean, I'm afraid errors may occur. We convert it to VDB. We use VDB here. Keep the voxel size as 0.1 for now. Drop a VDB combine. Connect them like this since we need to remove the intersecting part from the initial state. Change the operation to SDF difference. Okay, the intersecting part has been cut off. Then convert it into polygons. Show the terrain and take a look. One more thing needs our attention here. Take a look at the bottom. Do not make the initial state intersect the terrain. Otherwise, the terrain will leak water during the simulation. Shrink the polygons inward a little bit. This way, water won't leak during the simulation. Return it back a little. It's good now. Alright, we've finished the initial state. Next, we start to set the source. Back to the object. Jump back to frame 1. We use this shelf tool. Hit this object. Hold the Control key down and click this tool. Click this object and hit Enter in the view. Then the workflow is built. Here it is. This is for rendering. Hide it. This is the node for DOP data import. Hide it as well. Put them here. Dive into this geometry and check the source. Here's the created source. You can choose to use shelf thickness or not per your preference. It's merely to enlarge the source. I don't really need the source to expand because it will penetrate the terrain. Right now, the source may have already penetrated the terrain a bit. To avoid intersection, lift up the source a bit more. Okay, input point 1 here. Next, we give a velocity to the source. It doesn't have velocity now. Drop a point velocity. Add a velocity of this direction. Set it to 1 for now. It doesn't need to be big. Now it has the velocity attribute. Show the velocity lines and take a look. We need to alter here to keep incoming to keep its original velocity, that is no velocity. Then there will be only the velocity of the direction we added just now. The current velocity lines are a bit short. Now it's noticeable. Then add a curl noise to make it a little random. I don't want the noise too broken. Let's adjust the swirl size. Reduce the scale a bit. Alright, done with the source for now. This node is useless, delete it. The source and the initial state have been set. Enter DOP. Delete this. We first import the collision object. Here it is, which is the merge of the terrain and the rock. Create a null node and hit this tool. Select this object and press Enter in the view. We can see the collision source has been created. Since this collision object has no movement, we don't need the file cache node here. Then take a look at the VDB. The resolution is too low, so lower the voxel size to get a proper resolution. It'll be good enough as long as we can see the grooves on the terrain since they'll collide with water. Lower voxel size a bit more so that the grooves can appear. The voxel size looks good for now. Then go back to DOP. Press L key. Merge 2 is useless, delete it. As for merge 1, alter it to the second mode. Left inputs affect right inputs. That is, only let the collision object affect flip. The sim will be faster than in mutual mode. Retain other parameters in default for now. Come to the output here. The output workflow has been created. I don't like using it. Here I'll introduce my preferred workflow of creating flip. Before that, let's check on these two nodes. This one is to import flip data. This one is to pack particles, which means to convert them into packed primitives. And then output the cache. This way can save the disk space, but when they're imported again, they will be unpacked through the unpack points node. If the quantity of the particles is pretty large, unpacking them will really take a long time. So normally I don't use this function as it will slow down the simulation. However, if your disk space is not enough, you can check it. Here I turn it off. Next, let's cache the flip. Oops, sorry, I forgot one thing. The initial state has not been imported. I've only imported the source. Display particles as pixels to make the observation easier. The box of the flip solver is a little too big. We can shrink it a little bit. Do you remember the box I said before? It was to connect the box of flip solver. Let's connect them. Then import the initial state. Alright, it's done. But now it has no velocity. Check initialize velocity. Set the initial velocity with the same direction as that of the source. we still need to set the closed boundaries. Currently, there's no collision object at these boundaries. The fluid will definitely fall off the sides during the simulation, so we need to close this box. We only need to close it on these three axes: positive and negative x-axis and a negative z-axis. Then the fluid will flow only forward instead of streaming down off all sides. Since it's in testing phase now, it's unnecessary to sim the whole range. We can scale the range down a little to speed up the simulation. This is a sort of an optimization. Okay, let's narrow it. Here we will simulate flip in this area. In the final simulation, we will use the whole area. This scope is just for testing. We move this box to where there is a collision object. In this way, we can check on the collision dynamics of fluid and the rocks. Alright, done with the testing scope for now. Let's check the source. You can see that the size of the source has also changed. This is the pros of procedural control. Then let's go back to DOP and check again. Everything's good. Let's simulate it. But for that, we need to reduce the voxel size. The current resolution is lower compared to this human model, while the final simres of flip is supposed to be higher than it. Considering we are in the testing period, just increase it slightly. Of course, the closer the simres is to the real world, the better the simulated details will be. Okay, voxel size is good for now. Keep other parameters in default temporarily. Still take add velocity attribute for better observation later. We'll turn on other attributes in the final resolution. Since it's in the testing period now, if all are on, it will slow down the simulation. This is also an optimization tip. Then make it double check. Everything looks good. Alright, we can cache flip. Here I use this flip cache node I made before. Let me explain it briefly. We compare it with the original file cache. This node exports these three fields in DOP, which are particles, surface, and velocity. All of them will be needed. However, Whitewater simulation later will only require surface and velocity, not particles. If they are in one cache, when we export this cache later, it will also load particles. This is unnecessary and will slow down the production workflow. So to avoid this issue, I will cache those three individually. From here, they are separated. This is the surface field. This is val. These two are cached out separately from here. File modes are write files. Here, the attribute wrangle reads the particles of the first port. Remove print written here will not delete the particles because it runs in primitives. This expression is mainly to refresh data. The second and third ports of this node are connected to the caches. The data of the caches needs to be refreshed at every frame. In this way, all the frames can be cached into a disk. So this expression is just for data refresh. These are to cache particles. These two are to import the caches above. File modes of them are read files. These are the cached particles. The cache path can be set per your personal preference. These common parameters are promoted to the outside here. Okay, so much for this asset. This asset has 4 output ports. The first is particles, the second is surface, the third is val, the fourth is the merge of them. They can be exported individually later, which can greatly save time on loading unnecessary data. Thus, the efficiency can be improved a lot. Okay, we use this to cache flip. The path is good. We cache it from the first to 400th frame, save the project, and then cache to disk in the background. I prefer caching in the background because we can still operate the project during the caching process. Also, we can watch the result while caching. If anything goes wrong, we can stop cache in time. In this episode, we mainly set up the Flip workflow and cached a version of Flip. Let's watch it in the next video. See you in a bit. In the last video, we made the Flip workflow and cached Flip dynamics. In this video, we mainly talk about how to sim an intended Flip dynamics and explain the functions of some parameters on Flip solver through the tests. Let's first take a look at the previous dynamics. I cached all the frames mainly to watch the dynamic changes of the Flip. Currently, the dynamics has some issues. The falling water in the reference here is arc-shaped, but the simulated water seems to adhere to the terrain. The other half of the waterfall would also be like this. So this is the first issue needs to be resolved. Another one is that the water near the source flows backward. I guess it will be a lot of foam here when we sim the Whitewater later, which is not what we want. Thus, I'll remove it. So currently we have two issues to be settled. Let's talk about the first issue. There is surface extrapolation in Flip solver. We can check out Houdini documentation for its explanation. Find the Flip solver node, then collisions below. Here it is. It says this parameter helps fluid flow smoothly along the curved surfaces, but it can create a slight stickiness. Decreasing this value can create more dynamic splashes from collisions. Let me explain it with a brief sketch. In my personal understanding, it is the adhesion of water. Suppose it's a small ball here. When water flows down, the water flows along the surface of the ball due to the adhesion. Even if the water arrives at the right side of the ball, it will still continue flowing along the curved surface instead of falling down. The larger the value is, the stronger the adhesion of the water will be. Thus, the water seems to adhere to the terrain. If this parameter is reduced, the documentation says that there will be more dynamic splashes. Then, in the simulated effect, the force of the water adhering to the surface of the ball will be reduced. The water may start to fall at this point. In my understanding of the parameter, it's better not to set it too large. We can try lowering it a little bit. Set it to 0.1 for now. We will test it later. The second issue is that the water near the source flows backward. It's mainly because the velocity of the source is not high enough. Let's try adjusting it to 2. This is to make it flow forward faster to avoid the backflow somewhat. Since the velocity of the source was increased, the velocity of the initial state also needs to be increased. Let it be the same as the velocity of the source. Otherwise, the source and the initial state will collide and thus causes the backflow. Additionally, raising the velocity may also resolve the first issue somewhat, since the low velocity can also make the water flow along the terrain closely. Currently, we just order these two parameters, then we cache it for a test. I'd like to duplicate a Flip cache, save the project, then cache in the background. This is the result of the cache. We can see the first issue is solved. This is the first version of the water dynamics. The falling water adheres to the terrain. After the modification, there is a distance between the falling water and the terrain. I did not sim all the frames since this issue had been solved during the simulation. Well, through the tests, we can see the functions of the two parameters. The next issue is the backflow of the water near the source. Currently, there is less water flowing back than before, but we have not stopped it completely. So we need to adjust it further. Get into depth first. Actually, we don't have to lower this parameter too much because we still want to keep the adhesion of the water, making the falling water a little bit closer to the terrain. So set a moderate value here. We will test it later. Then we focus on the second issue. The initial state is a little high, but the level of the emitted water is lower and thus generates the small pit. That is the height difference between the initial state and the emitted water. When water flows, the emitted water pushes the initial state forward, and the initial state also pushes back the emitted water. That's why the water flows backward. So we can lower the height of the initial state. come up to the initial state. We need to make it lower. Before running this Boolean operation, we lower the height of the bound. That is to cut off the top of the initial state. Currently, the heights of both sides are different. I'd like to make them a little even. Add a transform. Rotate it along the x-axis. Thus, the heights of two sides are roughly similar. Lower it further. Almost like this high. Now it's lower than the source. Then I'd like to adjust another parameter, that is the initial velocity of the water. Raise it a bit. This may avoid the backflow of the water caused by the collision between them. We stop adjusting for now. Let's simulate it again for testing. In this simulation, I found an issue. We can see that the collision between the emitted water and the initial state causes some large splashes. If we continue to sim the Whitewater, there must be a lot of foam here. This is not what we want, so we need to settle it. The splashes are caused by the gap, so let's remove the gap to avoid the collisions and the splashes. I rotated the transform just now, so it generated the gap here. Move transform a little bit toward the negative z-axis, negative 0.2. The gap is still there. Move transform backward further, negative 0.5. Now it's good. They overlapped a little, but it doesn't matter as long as there's no gaps between them. Then we simulate it again. Cache it in the background like before. I didn't cache all the frames either. Comparing it with the previous dynamics, we can see the obvious difference. After the modifications, there's no more splash. The dynamics of the water are much more stable, and there's no more backflow. So this is exactly what I want. Then let's check the issue that the water flow adheres to the terrain. Take a look at the first version. The water adheres to the terrain completely. Then the second version, the one with surface extrapolation at 0.1. Basically, the water doesn't adhere to the terrain. Then the third version, I stopped it in the middle because of the splashes. This is the current water dynamics. We can see the water dynamics is changing during the sim. When the water just starts flowing down, there are some arched shapes here, but after a while, the falling water tends to adhere to the terrain. It is a little similar to the first version in some way, so I will reduce this value a little bit. Try 0.2. After previous testing for several times, I think 0.2 is proper. Then we keep this parameter for now. In the next video, we'll go on testing some other parameters. Thanks for watching! In this video, we will continue to adjust the flip dynamics. We will mainly focus on the key points below, max substeps in flip solver, velocity smoothing, adding noise to enrich details, simulating with a high res, and adding boxes to kill particles. Let's get started. Why do we test max substeps? Personally speaking, it's pretty necessary. In many of my project experiences, I find some simulated effects are good when I set max substeps to 1, and the simulations are very efficient. So sometimes we can speed up simulations with it. Basically, I tested it in my every project. If the simulated effect is acceptable, I will set max substeps to 1 to simulate flip. To improve work efficiency, we may have a try. The main thing is to test the max substeps of 1 and 2. Here I cached two versions. Version 4 is the simulation when max substeps is 1. Version 5 is the simulation when max substeps is 2. We can notice some differences between these two flip dynamics. Version 4 has some stripped texture on the surface of the water, but the overall difference is not pretty obvious. Let's take a closer look. This is the effect when max substeps is 1. There is some stripped texture on it. To watch it more clearly, convert it to polygons. Here we apply the second port, surface, alter it to polygons. Now it is easier to see the details clearly. This is the effect with max substeps of 1. On the water surface, there is some stripped texture. Cache 5 is the effect with max substeps valued at 2. The comparison shows that cache 5 has a smoother surface. That's the difference between them. When I tested the effect at the beginning, I simulated a flip with a relatively lower res and a max substeps valued at 1. It was hard to catch the details. Then I tested it with a higher resolution. The stripped texture on the water became very noticeable. So did this kind of piece. But there is no such a dynamic characteristic in the reference, so setting max substeps to 1 is not suitable for this project. But we can try it in other projects and see if the effects are acceptable, since the simulation with max substeps of 1 is much faster. The caching time is 24 minutes when max substeps is 1, and the time is 42 minutes when max substeps is 2. It saves almost half the time of the later one. If the tested effect is okay, it will be a lot more efficient. So this parameter is worth testing. We don't need stripped texture, so let's set it to the default value. Then we tested the next parameter, velocity smoothing in flip solver. This is also a common parameter. The larger this value is, the smoother the surface of the water is. That's to say, it's used to smooth the surface. If we need much simulated details of flip, we can lower it. Let's have a test on this parameter. This is the simulated flip. Here we are not going to see its dynamics since it's almost the same as before. We can compare it to the previous cache 5, which is the effect when velocity smoothing is 0.1. This is the one with velocity smoothing of 0.02. Overall, there's no noticeable changes, just some slight changes. In the areas where the waves are rolling, there are a little more details than before. Observing the color distribution of the flip surface, we can see the color of the adjusted flip surface is a little richer, so lowering velocity smoothing brings more details. But it's not enough yet, so we need to add a noise. Also, by raising SimRes, we can obtain some more details, but we can test it later. Now we first add noise and see how it goes. But for that, let me roughly explain the idea. First, we add a noise to the entire surface of the water. Then we need to strengthen the noise in some areas and weaken it in somewhere else to get some variation of the strengths. For a better observation, I'll demonstrate it with a grid in SUB. Roughly fit this grid to the flip to be simulated, raise its subdivision. We can regard it as the surface of the water temporarily, and then add and adjust the noise in VOP so that we can observe the color directly. After getting a proper color distribution, we can copy it to DOP, put down a color noise, connect them together and take a look. This is its default pattern. When we play the animation, it's frozen. Here we need to animate it. Add a vector to vector4 node. Choral noise can read the data outputted from this node, connect it to time. Now this noise has an animation. If we think the animation is too fast, we can slow the speed of the noise here, multiply time by a value. But I think the current animation of the noise is good. As said before, we need to strengthen the noise in some areas and weaken it somewhere else. Then we need two choral noises. Note here, we need to avoid the choral noises affecting the water dynamics too much, otherwise it won't look realistic. So we mainly add small-sized noise here, raise the frequency of this noise, so that the texture of the noise becomes small. We also need a larger noise. Lower the frequency of this noise. reduce the roughness a bit, so the color blocks become larger. Then we multiply the large noise by the small one to strengthen some parts of the small noise and weaken somewhere else of it. Drop a multiply node. Now we get some variation in noise strengths. Here's one more thing we need to note. Look at these numbers. We can see some numbers of the current colors are negative, both in the large and the small noises. But multiplying two negative numbers equals a positive number. In this way, the small noise will change too much, and in some areas of it will be inverted. This is not what I want. I just want to vary the strength of the small noise slightly, so we don't need the negative numbers of the larger noise. Add a length node, which converts vector to float. In this way, the values of the large noise can be mapped to 0 to 1. Then multiply length 1 by the small noise. Compare the result with the original small noise. This is exactly what we want. Then we can adjust the large noise strength a little, add a fade, tweak source max slightly. We get the intended effect now. Copy it into DAB. Here we add a pop-up. Paste here the network we made just now. Connect it to time. Output the result to force. Then let's similarly flip again and see how it goes. The red one is the flip with noise. We can see there are a little more disturbances and the color details on the surface of the water. Pretty obviously, there are more details now. A small noise is fine in this case. If the noise affects the flip too much and it causes unnatural dynamics of the water, then the dynamics won't be realistic. So it's the thing to note when adding noise. As for the intensity of this noise, we can adjust it further according to the needs. Well, we're done with adding the noises. I'd like to sim it with a higher res to see the effect later. Let's see the parameter friction. We also need to tweak it a little bit because there's some friction between the flip and the rocks. If friction of flip is 0, then friction on the collision object won't work. So raise it a bit. Lower the friction on the collision object a little bit since 1 is too large for it. It probably makes the water stick to the rocks or flow very slow. That's not good. A small value is fine. Then raise the same res and simulate it again. Since this is not a close-up shot, we don't need to make it too high. Then we add boxes that kill the particles. There are the boxes on both sides. This terrain is to kill falling particles. But after a few simulations, I found that the particles were killed when they hit the bottom of the fluid box. So we don't need this terrain. Disconnect it. Keep those two boxes. Why do I place these two boxes? In a real situation, there still should be a part of terrain on this side. When the water flows to here and it hits the rocks, the water will bifurcate and flow to both sides. But the simulation boundaries are closed, which leads to the water gathering here. So we can make an opening right here to reduce the water gathering. We can see the water level here is a little bit higher, that is, the water is a little much. So I made an opening here to make the water bifurcate. I added another one on the other side as well. We import those two boxes first, drop a pop group, switch to bounding object. Then we can use the two boxes that we created in SUP. Let's go back to the first frame and take a look. Enable dynamic simulation. Connect pop group 1 to the node below. We can see the two boxes are imported. In fact, all particles in these boxes will be added to this group. Type a name for the group, then we delete the particles in this group. Drop a pop wrangle to delete the particles. We use remove point. Port 0 is to be deleted. This way we can delete all the particles in the group. We have raised the simrest before. Let's simulate flip again. This is the effect with a higher resolution and the two boxes that kill particles. Obviously, the details generated by the collision between flip and the rocks are much richer. There are also some rolling waves. Exactly, there are a bit more details than before. Flip dynamics becomes much richer. It looks good. In this simulation, we used a higher simrest and the boxes that kill the particles. But which one affected the dynamics greater? To make it clear, I'll test it. This time I'll keep the same simrest but remove the boxes and then simulate it again. Disable both nodes. Then let's simulate it and see the effect. I only simulated flip in part, but we can already see the difference between the two simulations. The right one is the effect without the boxes. Obviously, there is no rolling dynamics in the collision areas now. This comparison proves that the boxes bring the effect of rolling dynamics. Enable the boxes. Then let's go through the parameters under these two tabs. We'll add these attributes when simulating the final effect. It's in testing phase currently, so we don't add them for now. Otherwise, the simulation will be slowed down. Let's talk about reseed particles. It's used to count the number of particles inside each voxel, then delete particles in two crowded voxels, and create more particles in sparse voxels. But when turning it on, the calculations are quite large. So we can turn it off and see if the simulation can be speeded up. If it speeds up the simulation and it makes little difference in effect, we can turn it off. Before the test, we lower the simrest to speed up the simulation a bit. Set it to 0.05. Then we cache flip once with reseed particles on, and cache again with reseed particles off. Make two copies. One is on and the other is off. Then we test the time they will take. The left one is with reseed particles on. The right one is with reseed particles off. There's no obvious dynamic difference between them. The left effect takes 1 hour and 3 minutes. The right effect takes 52 minutes. The right effect saves 10 more minutes. It seems just a short time, but when we sim the final effect with a high res in the whole range, it will be a lot faster. So we turn off reseed particles. To speed up the simulation, here I'd like to test two more parameters. This is use deforming geometry in the collision object. The role of it is to use dynamic objects. Since the current terrain is frozen, it's unnecessary to check it. Then the simulation will be speeded up a bit. Besides, here is use OpenCL in Flip Solver. If your GPU is pretty good, you can check it. It can also speed up the simulation. For other options, we don't need them currently, so we won't test them here. Then we test the two parameters modified just now and see how much the sim can be speeded up. This is the effect with OpenCL enabled. The dynamics is not much different than before, but it took 7 minutes longer. Maybe this parameter doesn't do much for speed up, so we turn it off. We can see some splashing particles where the water collides with rocks. If they fly too far, we can add a drag to limit them a bit. The current flip looks good, so we can go on to render and composite it for a test. In this way, we can know the composited picture earlier, which is conducive to examining if the overall effect is good or not, and to spotting the problems to be fixed further. It's unnecessary to spend too much time concentrating on simulating effect. Only after compositing it, we can see the final picture, thus know better where it needs to be modified and promoted. This is very essential. Also, some unnecessary work can be avoided effectively. When the effect comes out 60% or 70%, you can give it a go. Now we are going to add the attributes that we need later and then simulate the final flip of the whole range. In the end, we'll sum up the key points about the flip simulation. Get insight up. We first check the attributes that we need. Toggle on ID attribute, because later we'll use ID attribute to delete particles to avoid flickering. The others in this tab are not needed. Check rest attribute. When adjusting materials later, I'll add a displacement based on rest attribute to enrich details on the surface of the water. Basically, these are the final required attributes. The others are not needed. Toggle off OpenCL here. So much for the attribute setting. Then change it to the final simRes. Scale up the fluid box. Select this box. Jump to the top viewport and fit it to the terrain. This is the range of the final simulation. Let's check it. The source is matched well. Back to DOP. Sim a frame and take a look. It goes well. So the flip has been set properly. Let's cache it. This is the final effect shown by the well visualization. I think it looks good. Alright, let's briefly sum up the previous episodes. First of all, about the flip simulation. 1. How to solve the issue of the falling water adhering to the terrain. 2. How to fix the problem of the water flowing backward near the source. 3. The pros and cons of mix-up steps. 4. About the velocity smoothing in Flip Solver. 5. The workflow of adding noise. 6. The impact of the boxes that kill particles on the flip dynamics. These are about flip settings. Let's move on to the terrain settings. The velocity of the flip source and the slope of the terrain can affect the distance between the falling flip and the terrain. You can adjust it as needed. The relief of the bevel and the relief of the uplands are the main factors to affect the water dynamics. Also, the shape of the bevel determines the shape of the falling flip. We can see there are arched shapes at the bottom of the falling flip, which helps get a good lighting effect and brings some sense of layering. This is a key point. One more thing. In the process of flip simulation, we should take lighting into consideration and check if the simulated flip is layering. Personally speaking, this is pretty crucial. Do not always struggle with the details of flip dynamics or other aspects alone. Instead, we should focus on the overall effect. Last but not least, let's sum up how to optimize flip simulation. 1. Cache particles, surface, and velocity separately. 2. Carry out partial tests and find out problems timely. 3. About the receipt particles. 4. Add the required attributes before final simulation. These are the key points to speed up the simulation. That's it for the summary of the previous episodes. So far, we're done with the flip simulation. We'll continue with the project in the next episode. Till then, this is the final simulated flip. Delete all these previous versions. In this episode, we are going to convert the flip to mesh. There is a default node in Houdini to deal with it. You can choose particles here. All the particles are converted in VDB from particle fluid. Think about it, it's a huge amount of calculation. Currently, the count of the particles is over 12 million. If all the particles are converted with this workflow, it will take a very long time. Here, I won't use it. I'll talk about a new one. We can see clear details where water collides with the rocks and in the high vorticity areas on the surface of the water. Alter the display mode. Now vorticity is visualized. As seen, there are plenty of details in these areas, while in the low vorticity areas the details are few. My idea is to extract the particles in the high vorticity areas and the areas where the particles collide with the rocks, and then convert them to high-resolution VDB. For the smooth areas where details are few, it's fine to convert them to low-resolution VDB. VDB from particle fluid is for converting, Here is it in a node. The greater the number of the particles, the longer it takes to convert to VDB. So we only convert the particles in the areas with rich details and exclude the smooth areas, which will save us a lot of time. Now we extract the particles in the high vorticity areas and the areas where they collide with the rocks. But firstly, we need to optimize flip, since it's not needed to include all the particles. We can see there are two layers here. The lower surface of the water close to the terrain is invisible in the camera view, so it's unnecessary to be calculated. We can delete it. In a word, we optimize the particles first and then convert them to VDB. Optimizing as much as possible can improve the efficiency a lot. This is the particles cache. This is the surface field. We will use them later. Now we remove the particles on the lower surface of the water. Here we can select them by the terrain because they are close to the terrain. We import the terrain that was created previously. Here it is the extruded terrain. Import it. Then create a group to group these particles. Select point mode, then rename it. We call it Del. Select bounding object. Now only part of the particles on the lower surface are selected, so we need to expand the terrain a bit more. To avoid errors, we convert the terrain to VDB first. Drop a VDB from polygons. Then we convert it to polygons. Add a convert VDB. ISO value is to expand mesh. Raise it slightly. The particles on the lower surface are selected now. Then we delete them. Drop a blast. Assign Del. Now they are deleted. Make a compare. Nearly half of the particles have been optimized. Here, these particles are deleted accidentally, but it doesn't matter. They don't need to be converted to high-resolution VDB. Here, I'd like to share a tip. Some people may use attribute wrangle and type remove points inside to delete particles. Please note here, if you want to remove a large number of particles, I recommend the blast node. Currently, the number of particles is quite large and approaches millions. It will be pretty slow if we use attribute wrangle, but it's very efficient with blast. Here, we group the particles that need to be deleted, then use blast to delete them. If you want to use attribute wrangle, you can group the particles in it and delete them with blast. It will be way more fast. Let's go ahead. Actually, we don't need these particles around the source because they won't appear in the camera view, so we can delete them. Import the bounding box of flip. Here it is. I'll put box 1 into a non-node. Then copy it. The range is exactly aligned with the edge of flip. We can remove these particles with the function. Select points. Rename it. Now we need to get the scope of the bounding box and define an axis to be controlled. Here we use a function, rel.bbox. The first is the serial number of the port to be read. Here it is 1. Then position. Then define an axis. Here it is the z-axis. Now we got the mapped range of the z-axis of this box. Then we use ID to delete the particles, which can avoid flickering. We input ID in the front, and use a ramp function to map the ID of all the particles to 0 to 1. Here we want to control this range with the ramp curve. Define a name, input a comma, then end it with a parenthesis. Click on this icon. I forgot to add here since ID is an attribute. Tweak the ramp curve. Now the corresponding particles are added into this group. Then we remove these particles. Adjust the ramp again. Almost like this. I'd like to delete them in a gradual way. This way there will be a transition. Since the box is not wide enough, these particles are not deleted. Let's adjust the boundary slightly. As the negative z-axis, raise it a little bit. It's okay now. Next, we delete the particles on the smooth surface of the water. Duplicate these two nodes. Delete this one and add a new one. Here we delete the particles based on vorticity. For easy control, I bring up a slider. Let's delete them. The expression is to delete the particles in the areas where the vorticity is less than this value. I'd like to keep some more details, so it's not needed to delete too many. Then we check the part of flip that collides with the rocks. We can see if we delete particles based on vorticity, some particles that collide with the rocks are also deleted, thus some details are lost. Actually, I want to keep this part of flip that collides with the rocks, so besides vorticity, we still need another condition. My approach is that since the water that collides with the rocks is pretty sparse, we can use the surface field. Let's see how it looks first. Here it is. We shrink the surface inward a bit first. Select Erode. We can see the areas where the water is sparse disappear, while the areas where the water is thick are basically as they were. Then expand it outward a bit. As seen, only the areas with sparse water are affected. The rest areas are still the same as they were. So we can remove the particles in these areas. Here we need one more condition. We use volume sample. The first part is sampled and the serial number is 0. The data imported from the first port only has the surface field, no other fields, so we just type 0. Then position. After being shrunk and expanded, the sparse areas of the surface field disappeared. If the particles are outside the current surface, then they need to be kept. I'll put a value, which makes it easy to be adjusted. Then connect this port to the processed surface field. To observe clearly, display it separately. We can see these particles are sampled in the processed surface field. After deleting these particles, the rest is what we want. Grab a blast, then we get the areas where the water is sparse. But now the result is not right. Let's modify the calculation type of the two conditions. Change it to AND. That means only when both conditions are met can the particles be deleted. Because of the vorticity condition just now, some particles that collide with the rocks were also removed, so we need AND here. Let's make a compare. Some particles are still removed. Alter this value slightly. Okay, now the areas with sparse water are kept. Alright, until now we have optimized the flip. These are the particles to be converted to high-resolution VDB. We use VDB from particle fluid in this node. Let's adjust these parameters. This one controls the resolution. I recommend keeping it consistent with the simres of flip, which is 0.03. Set it to 0.03. We tweak the parameters properly based on how many details to be presented in the camera view. If the simres is too high, the simulation will take a very long time. Actually, the current particles are a bit too large. This one controls the scale of the particles. We reduce it a bit. Now the VDB looks more exquisite. But I still want more details. We can modify this parameter. It controls the maximum distance at which particles interact. The higher the value is, the smoother the particles effect will be, like here. If that is too much, there will be less details. Down it a little bit. We can see now there are more small VDBs, that is, the water has more details. But this value shouldn't be too small either, otherwise the effect is also not good. We order it according to the shot, then convert it to polygons. Let's see the effect. We can then adjust these parameters in detail based on the effect of high-resolution areas. Currently, some sparse VDBs are basically invisible. This parameter controls the scale of the voxel. Lower it a bit. We can see the details of the VDB are more obvious. The smaller the parameter is, the more details of VDB will be shown. Meanwhile, the slower the caching will be. We adjust it based on the shot or our needs. Besides, when we simulate Whitewater later, some areas of VDB will be covered, so we should consider comprehensively to tweak it. The water here is not very noticeable. Let's expand it outward a bit. Now these details become more apparent. Increase it a bit more. It's better. But there comes a problem. These splashes are a bit spherical and like little balls, which doesn't quite conform to the characteristics of water. Add a peak node below. Shrink the water inward a bit. Now it's quite similar with the surface tension of water. So we can tweak distance to shrink or expand water to get more details. Now the high-resolution flip has been converted. Let's merge it with the low-resolution surface. Plug the high-resolution VDB into the first port because the resolution of the second port matches that of the first port. This way the result will be correct. Select SDF union. Now both are merged together. But there comes another issue. The surface field covers the high-resolution VDB, so we need to adjust it further. Shrink the surface inward a bit. We can preview it. Lower the offset a bit to remove the high-resolution areas. We can see now the high-resolution VDB is more noticeable. Then let's see the upper surface of the water. Like here, a small part of the high-res VDB is still covered. Increase it slightly. It will shrink inward a bit more. Tweak it again. Now the details appear a bit more. But this value should not be too large either. Otherwise, there will be some gaps between the VDB and the surface. A proper value is fine. We just need to make sure the gaps between them are not too obvious. Now the effect is okay. But there are some small-sized VDBs on the surface which are high resolution. Let's convert it and take a look. Now there are some spikes on the surface of the water. These are small-sized VDBs. When rendering, there will be some flickering on the surface of the water. So we need to handle this problem. Drop a VDB smooth to smooth the small-sized VDBs. But I don't want to smooth these splashes. Here we can use them as the mask. Drop a VDB from particles. Now nothing appears. On one hand, the resolution is somewhat low. On the other, the radius is a bit small. We adjust them further. Reduce the radius a bit. Now it appears. We don't need the surface field. Turn on Fog VDB, then connect it to VDB Smooth. As we can see, it is inverted. Reverse the mask. Compared with the previous effect, it still loses some details. Let's adjust the mask further. To keep these details, we increase the radius slightly. Actually, we mainly want to smooth the upper surface of the water, not the falling part. Let's go on dealing with these particles. We can delete the falling part. Create a blast to delete the particles where the height is less than 3 meters. Alter the height. OK. We use the current VDB as the mask. Reduce the particle radius a bit. Currently, the smoothing areas are outside the mask. We need to invert the range of particles. Make a copy of blast, then invert it. Connect it here. Toggle off the invert. Let's make a compare. In this way, the spikes on the surface of the water disappeared. Meanwhile, some details are kept as well. We can tweak the radius to get a bit more details. We can see the details are slightly more than just now, because the smaller the radius of the particles, the smaller the areas where VDB is smoothed. Then more details will be retained in the end. Now we have finished the conversion. This is the final VDB effect. Lastly, convert it to polygons. This is the ultimate mesh. We can preview this effect and check if it's okay. If yes, we can cache it from here. I think it's good. So let's cache the VDB here. If we ensure this is the final effect, we can cache it here. This way, these nodes above won't be calculated, which can greatly improve the efficiency. In addition, this node is just to visualize flip. We don't need it here. Currently, the conversion has been finished. Remove this unused node. Now we cache it, but not all the frames. We only need the part when the water is stable. The water stabilizes at about the 200th frame. So we start from the 200th frame. Rename it. Change the color. I modified the path just now in order to make the hierarchy a bit clearer. I prefer to render every 2 frames, which can increase the caching efficiency. Actually, I tested it before. The render effect is acceptable. So we choose an effective way. Actually, in many cases, we can consider skipping frames when caching, but it doesn't work in DAB because in DAB, every frame needs to be solved. Well, it's all up to your needs to find possible ways to improve efficiency while keeping the effect. Then let's start caching. This is the VDB cache. You can make it flipable to check if it goes well after caching. I've already checked it, so we skip it now. Let's go on. This is the mesh converted in the last episode. Here I tweaked this parameter again, down it a bit. This way there will be more holes, thus more details. I removed the peak here because it makes some droplets disappear. We apply it accordingly based on different projects. Alright, I think the current effect looks good. Next, we need to remove the part around the source and both sides of the water. Similarly, we can use the bounding box of flip. We apply this function to delete particles. Here we use it again. I've created an asset. Here I directly use it. The first port needs to be connected the object to be deleted. The second port is connected to the bounding box. This way the sides have been removed. Actually, the method used in this asset was explained in the last episode as well. That is the real point B box. The principle is the same, just the directions are different. Actually, it's the same function. I have explained it before, so I'll simply skip it now. Then it's set in different blasts for different axes. That's it. These axes are taken out for easy adjustment. Here we just need to delete the negative z-axis as well as the positive and negative x-axis. Toggle off unused axes. This part is not cleared completely. We still need to adjust the bounding box. Drop a bound. We need to delete more on z-axis and less on both sides. Then we need to whiten the bounding box on x-axis. A bit more. Besides, in the step of convert VDB, we can optimize it a bit more. Switch to flat wire shaded. This parameter can optimize the mesh a bit slightly, so that in some smooth areas, the count of polygons can be reduced. Thus, PC can run a bit faster. Now we got the optimized mesh. I want to delete some more around the source. Alter here. These two parameters actually represent these two control handles on the ramp here. The method is the same as before. We just take out some parameters. The polygons on both sides are deleted a bit too many. Whiten these two sides again. Now it's okay. Then we need to remove the lower surface because it doesn't need to be rendered. Show the terrain. We can see the lower surface and the terrain are interlaced. Many areas of the lower surface are exposed above the terrain. When rendering, there will be a lot of bright blocks under the water. This is an effect I rendered before. I'd like to explain this issue with it. We can see there are some bright blocks because the lower surface is not removed. Actually, it looks abnormal, so we need to remove the lower surface of the uplands. For the falling part of the waterfall, it's unnecessary to remove it. I've tested it before. If I retain the mesh here, there can be brightness contrast between the downstream and upstream water. Let's remove the lower surface of the water. To avoid affecting other parts, I prefer to group the areas to be deleted. We still use the terrain. Then we need to expand the terrain a bit. Duplicate these two nodes. Now the lower surface has been selected. Also, I want to remove the mesh that collides with the rocks as well to avoid bright blocks when rendering. Here, we need to import the mesh that the terrain is merged with the rocks. They are selected now. But please note here, we cannot delete them directly because there are extra polygons selected here. Even if we adjust the expanding range in detail, the problem cannot be solved completely. Like the water here that collides with the rocks is relatively sparse. It's hard to get a required result by this parameter. We need to consider another approach to remove them. I'll demonstrate it with a small ball. Change it to polygon. Increase the frequency. Shrink it inward slightly first. Then project. We project the ball onto the shrunk one. The direction is upward, so the lower surface is projected onto the shrunk ball, and the upper surface keeps as before. Reduce distance a bit. There is a create a point group below. We can remove the polygons in this group. Now the lower surface has been removed. We apply this method to our case. We still go with group 2 here. We can see almost the whole mesh is deleted now, which is quite different from the result with the ball. Let's check it. This is to shrink inward. This is the created group. Thus, only the lower surface of the water shrinks inward. Lastly, we project. As we can see, the upper and the lower surfaces are blue. This proves both surfaces are projected. Thus, they are added into the group and removed. In fact, this model is much more complicated than the small ball. However, the principle is the same. I'll explain it by sketch. This is the side view of the water flow effect. Here I draw the blue and yellow lines. The yellow line is the mesh with the shrunk polygons in group 2. Here is the shrunk area. The rest is overlapped with the previous mesh. There is a short distance here. When we project upward, since the upper surface is overlapped, it will be added into the group in ray. Let's see the lower surface. The overlapped part is added into the group in ray as well. As for the shrunk part, it will be projected onto the mesh that applied a peak. So the whole lower surface will be added into the group. Thus, both the upper and the lower surfaces come into the group in ray. They are deleted in the end. So the upward projection won't work. Let's try projecting downward. The upper surface still comes into the group because it is overlapped. So does the overlapped part of the lower surface. But as for this part, when it's projected downward, there is nothing under the blue. So this part is not projected. Then it won't be added into the group. This way, the required area is selected. That's the difference between projecting upward and downward. Let's project downward now. Change it to -1. Here we need to reverse it. Now the lower surface is deleted. But there are some spikes. Because the ray node can change the original mesh. To avoid it, grab a group copy. Because ultimately, we just need the group in ray. We copy the group in ray to the previous mesh through group copy. And then delete it. Now the mesh is good. Next, let's check the areas where water collides with the rocks. As we can see, the loss of details is very minimal. We can adjust distance further. The smaller the distance, the fewer details it loses. Until now, we have finished removing the lower surface of the water. Previously, I tried using keep binormals in group created node to delete the lower surface, but the result was not accurate. When I tested this method, it ended up nice. There are some scattered points onto the mesh. Let's clean them up as well as the useless groups. This is the processed mesh. It doesn't have any attributes. Since rendering requires some attributes, let's transfer the attributes of the particles to it. We need rest attribute when we adjust materials, so transfer the rest attribute, that is in points. And in detail. Then transfer velocity and vorticity. These are the commonly used attributes. Now we have got the final mesh, then let's cache it. The frames to be cached need to be connected with the flip VDB1. Start from the 200th frame as well. Modify the path here. If it's your first time to make the project, I don't recommend caching all frames of the mesh or VDB sequences because the highlight of Waterfall is Whitewater, When you spend a long time caching both VDB and mesh but find the Whitewater doesn't look very well, you'll probably have to remodify the flip, since in most cases, the Whitewater effect depends on the dynamics of the flip. If flip is not good, the effect of Whitewater won't be satisfying. If you remodify the flip, then the VDB cache and the mesh cache will be in vain. So it's better to cache the mesh for one frame and check it first, and then test the shape of Whitewater to see if the simulation goes well. If it's good, we can render the final effect and check the result. If it is acceptable, then we can cache VDB or mesh sequences. This way, it can save much effort and bring better results. Let's cache it now. Thank you for watching. In this episode, we mainly focus on creating the workflow of simulating Whitewater and setting the Whitewater source. Let's begin with hitting the Whitewater on the shelf, get inside up, choose this node, then press Enter in the 3D viewport. Now we get a default Whitewater simulation workflow. This is the Whitewater source, this is stop, and this is the final Whitewater. First, let's set the Whitewater source. Since I use my own workflow to convert particles to mesh, the path needs to be revised. The Whitewater source only needs the surface field and the veil field. Merge these two. Then import node 3. Now there is the surface field and the veil field. Find a frame when water is stable. Let's see the Whitewater source. Solo it. By default, these three options are checked, which are three ways to extract Whitewater source. But not all of them are necessary for us. Setting Whitewater source properly is very important because it will affect the amount and range of Whitewater. Have a look at the reference. In the upper part of the falling waterfall, the Whitewater is not too much, and it gradually increases in the lower part. This is the distribution of the amount of Whitewater in the reference. So when setting Whitewater source, we need to note the amount and range of Whitewater should not be too large. Here we turn off them selectively. This option makes Whitewater appear on the whole surface of water, which is not what we want. Then acceleration. We reduce the range and see. Also, it makes the range rather large. This is not what we want either. The last one is vorticity. Let's alter its range. The source is still too much. Here we can find the speed range. It affects the control range of the three options. We can change the speed range to remove Whitewater source in the areas with low speed. The falling water pours with high speed, so we can control the source range through the velocity. That is to make the Whitewater source only appear in falling water. I usually add a volume mix, increase the post-modi, then the source is more obvious, which is easier for us to observe it. Sometimes we may think the Whitewater source in some areas is a bit less, so we will revise some parameters to make it a bit more. But after simulation, the Whitewater would be too much and look very thick without details. Though it seems the source doesn't exist here, in fact, it does. Here we can raise the thickness to make it a bit more obvious. This way, the simulated Whitewater can be avoided too much or too thick. Currently, I use vorticity to extract source. Basically, vorticity is quite high in the areas where water hits the rock, and also relatively high on the lower surface of the falling water, especially at the bevel of the terrain. But it's low on the surface of the water. It's workable to extract source by vorticity, but that's not enough, because Whitewater should also appear on the surface of falling water. We can try acceleration. Display it alone. Now the range is a bit large. We can see this is the contour of water. In the upper part, there is some whitewater source, but in the reference, the whitewater is little here. I want the effect in the reference, so acceleration cannot bring the intended effect. Actually, I want more whitewater source on the surface of lower part of falling water. Here we can use vorticity. In the reference, there are some white clusters when water falls, so we need to create another whitewater source. My idea is to extract the source where the water is sparse. Thus, the range will be smaller. This way, the whitewater won't be too much. To extract it, we need a surface field. Import the surface field here. We shrink it inward first, then expand it outward. Let's see the result. Then we delete particles in these areas. Import the particles first. Actually, we used the same way as before. Copy it. Here, vorticity is not needed. This way, the source is extracted. Now the range looks somewhat small. We can enlarge it a bit more. Now there's some whitewater source on the surface of the lower part. Like here it is on the lower surface. On the surface of the upper part, there's little whitewater source. This is pretty much what we want. Then we combine this whitewater source with the previous one. Convert these particles into volume first. Drop a VDB from particles. Now the source is not displayed because the resolution is too low. Reduce voxel size a bit and make it close to our SimRes. If still nothing is displayed, we can increase point radius scale. The current field is density. To combine it with the previous one, we need to match their names. Change the name here so that the names of these two fields are the same. Lastly, drop a VDB combine to merge them. Select Add. Now they are combined. This is the range that I want. Let's look at a few frames frontward. There's still one problem. That is, flip is not stable in the first several hundred frames. Like here. There is also whitewater source which is not needed, so we need to remove it. Drop a box. Put the box here. We need to delete the whitewater source inside this box. First, we convert the box into VDB. Add a volume bob. Sample the VDB of up input 2. Then we get the data of this box. The values inside the box are negative, on its surface are 0, and outside are positive. Then we can multiply these values by the whitewater source. To remove the whitewater source here, we need to make the values here become 0. Since 0 times any number equals 0, the whitewater source will disappear. Besides, we need to make the values outside the box become 1, so that the whitewater source will remain as it is. Import the whitewater source here. The name here needs to be the same as this name. Then multiply these two. Currently, the values inside the box are negative. Add a clamp to limit them. The mean value is 0 and the max value is 1. Then output it. Let's take a look. Now the whitewater source inside the box is removed, but the source outside is also influenced. The values on the surface are 0, and the outward values are from 0 to 1, because the clamp only limits the values above 1 to 1. There are values between 0 to 1 in some areas. After these values are multiplied by the source, the whitewater in these areas will be reduced. Add a ramp. Set the values outside to 1. Now the whitewater source is the same as before. The left handle controls the source inside the box. Now we can delete the source inside the box only. Besides, there is another problem. Since the water is dynamic, so are the areas in the box. So we need to keyframe the size and center of the z-axis of the box. Let's switch to the right viewport. We want to make the box only affect the upper surface of the water, not the lower surface, since the lower surface collides with the terrain in some areas. So we need to keep it unaffected, and only remove the whitewater source on the upper surface. From the 200th frame, the water stabilizes. Then this box is no longer needed. We can set a keyframe animation for the value 0 inside the box to make the box stop working. Otherwise, it will continuously kill the whitewater source inside the box. That is not what we want. Thus, set a keyframe around the 200th frame. Then after a few frames, set value from 0 to 1. This way the source inside the box won't disappear, but remain as it is. Let's have a check. The source inside the box before the 200th frame is removed. So this is the final whitewater source. We can cache it now. Here it's unnecessary to jump frames, because when we cache stop later, stop needs to read the cache data. If we jump frames to cache, there will be something wrong with the simulation. So we cache all of the frames. Now let's begin caching. Thank you for watching. In the last episode, we've cached the whitewater source. Now we are going to simulate whitewater. Let's see the dynamics of the whitewater source first. Everything goes well except for the cache at the first frame when there is a large piece of source. Sometimes we may encounter this problem. We need to remove this frame, or else it will produce a lot of whitewater later. Let's settle the issue by skipping the first frame, but it cannot be void, otherwise errors will occur. Here we can replace it with a second frame, that is, $f plus 1. Then the first frame is fixed. At the second frame, that is $f greater than 1, we switch it to the cache. Now the Whitewater source is good. Next, go inside dap. We first import the collision object, copy it from flip. Actually, they are the same one. Next, let's see the parameters of Whitewater solver. The Whitewater skill, I usually make it the same as the simrest of the flip so that they can match. As for the parameters below, I'll introduce them selectively. If the simulated particles are not enough, we can raise emission amount. It can increase particles as a whole. Lifespan below is the lifetime of particles. I'd like to bring it up a little. These three parameters mainly affect the shape of the spray. We keep them unchanged. The next is random seed. Also keep it as default. Then the aging rates for these three. Keep the default too. Next, we enable add noise, which can add some randomness and details. Reduce frequency a bit. Increase amplitude slightly. You can adjust them according to your experience. If there's nothing wrong with the simulation, meanwhile some details are added, then the values are proper. As for the next tab, we keep it default. Same to this one. Jump to foam tab. The parameter enable density control makes the Whitewater clump. If the particles are sparse on the surface of the water, enabling this parameter can clump these particles. But the effect is not very obvious where there are dense particles. Then let's talk about depth range. Here, density control works only in the depth valued from negative 0.75 to 0.25. Out of the depth range, it doesn't work. The depth range above controls the distance from the foam layer. Now it's from negative 0.8 to 0.8. Next, the ramp. The two handles at both ends correspond to the two parameters above. The middle one is the position of foam. Then constraint stiffness. It is promoted from the pop fluid node in Whitewater solver. You can test it in the pop fluid node to learn more about it. I made a few tests on this parameter. Here are 3 flipbooks with different values of it. Let's take a look at the effects. The larger the value is, the more obviously the particles clump in the sparse areas. While in the areas with dense particles, the effect of clumping is not noticeable and the spacing of particles is relatively even. If we set this parameter to 0, we can get the thread-like shape. This is the effect of the parameter. Besides, higher values will result in slower simulation. You can set it according to your needs. To avoid the particles being too scattered, I set constraint stiffness slightly higher. Also, constraint stiffness can be controlled by the ramp below. The highest value corresponds to the position of foam. When the depth is valued at negative 0.75 and 0.25, the stiffness is 0 correspondingly. With the ramp, we can control the stiffness flexibly. If you want to control more spray, you can increase this value. If we set it to 1, then it controls all the spray. We still keep this parameter as before. The next one is erosion. After enabling erosion, in the dense areas, particles will die slowly. In the sparse areas, particles will die quickly. We don't need it this time. Then let's see repellence, which give rise to cellular foam structures. We can solve a frame and take a look. There are some points above the surface of the water. Display these points. In simulation, every point can exert a repulsive force on the nearby Whitewater, thus giving rise to cellular foam structures. Feature size range controls the spacing of the points. Go inside to take a look. In this node, here is a grid and some scattered points. The size of the grid is the same as that of the bounding box. These points are projected onto the surface field, thus producing the effect of cellular foams on the surface of the water. Normally, the cellular foams appear on the surface of the water, but when the water falls, the repulsive force won't exist. So we need to make them only appear on the surface of the water. Nothing is displayed now. Let's check it out. Some points are already deleted by grid kill node. Disable this node. This way these points can be projected on the surface field. If you find there are no cellular foam structures, you can come here to check the issue, then revise it. Let's jump forward and take a look. We can see there are some scattered points on the surface of the falling water. Actually, these points are not needed. Let's delete them according to the height. Roughly 7.8 meters is okay. Wire +1 up. Pin 3D viewport. The spacing of the particles is related to density scale. Let's go back to DOP network. It is from the minimum spacing to the maximum spacing. We can see the spacing becomes denser, which will give rise to more cellular foams. You can adjust it according to your needs. Additionally, there is a parameter that can be optimized in the scatter node. Relax iterations. The higher the value is, the longer the calculation time is, so we can reduce it to a proper value to optimize the simulation. Meanwhile, these points will be more random, so will be the cellular structures. Then strength range. It is from the lowest strength to the highest strength. If the effect of cellular foams is not obvious, we can increase it. Noise range is to break up the edges of cellular foams. Every point has a repulsive force, but is average, so the cellular structures are rather smooth. Briefly, the noise range is to make the edges of the cellular noisy. We can adjust it properly to randomize the edges. The last one is to animate the noise. Increase it slightly. The following are advanced settings. Keep the values as they are. Then adherent. It is to adjust the force that the particles adhere to the surface. We mainly explain these two parameters. To make you understand better, I will demonstrate them with a simple case. This is an effect that a stone hits the surface of the water. We use it to simulate whitewater. Keep the default parameters for now and simulate it. This is the first version. You can see the particles flickering where foam and spray meet. If you find the same problem in your project, you can adjust these two parameters. The first parameter controls it through depth. Currently, particles in the depth between -0.6 and 0.6 are affected. The spray is included as well. So we can see the spray flies some distance, then immediately sticks to the surface field, which is rather abnormal. It's because the spray is subjected to control based on the depth. Let's see the bubbles under the water. They also stiffly stick to the surface field after going out a distance. This is the first version with default settings. Then we change it to 0.2 to reduce the control depth. Let's take a look at the second version. Obviously, the dynamics of spray and bubbles look somewhat loose rather than sticking closely to the surface field. This is because after we reduce the range of depth control, there's more spray unaffected by the adhesion. But in the first version, the control range is relatively large, thus producing some flickering. The second version looks better. The control range is smaller, thus the amount of spray and bubbles becomes larger. This is the role of the first parameter. Reset it. Then we talk about the second parameter, which is based on angle. Let's see the first version with the default setting again. Then increase it. Let's take a look at the effect. We can see it's different from the first version and looks loose as well. Here, let me explain it briefly. When a stone falls, the water splashes around. It is the surface field. Every particle has its own movement direction. Like some particles move toward this direction, some toward this direction. Let's say this is the direction of the gradient. Then the solver calculates the angle between the velocity vector and the gradient. If this parameter is smaller than the angle, then the particle will stick to the surface field. Suppose this angle is 85 degrees, this one is 25 degrees, and the parameter is 30. Since 30 is smaller than 85, then the particles with this velocity vector direction will stick to the surface field, but the particles with this velocity vector won't. If we set the parameter to 100, now it's larger than most angles. Then the particles that stick will be reduced. Briefly, the smaller the parameter, the more the attached particles. Likewise, the larger the parameter, the fewer the attached particles. This is the effect of the parameter. Let's get inside to see the code. It outputs data into position in the end. The code here is to get the gradient. There are two judgment conditions. One is the depth, and the other is the result of dotting the gradient and the velocity vector. If the result is smaller than the parameter, then the following code runs. This is how it works. These two parameters control the range that the particles stick. The range below corresponds to the control range. As for other parameters, we keep them as they are. So much for this node. Some particles in flip splash far. Since the Whitewater inherits the velocity of these particles, it will go farther. To prevent the particles going too far, we can add a drag node. Here I want it to only work on spray. We can use depth to control it. We set the depth greater than 0.1, then it's the spray above the surface of the water. Alright, let's start caching. Before that, we remove all the unnecessary attributes and groups first to save some disk space. We need to keep point attributes and vertex attributes. Delete primitive attributes and detail attributes. They're not needed now. Then clear up the unused groups. Here I'd like to delete all these groups because with depth a lot of things can be achieved. Now let's start caching. This is the current Whitewater. Let's set the display color. I usually use depth to control it because the particles have the depth attribute. Import it first. Connect the depth to color and take a look. The depth of the underwater is negative. Above the surface of the water, it is positive. Put down a fit. In Whitewater solver, the maximum depth is minus 0.8. So here we set it to minus 0.8 as well. Then positive 0.8. Map it to 0 to 1. Then add a ramp. Go backward and set the color. This is for the underwater bubbles. This is for the spray above the surface. Then set a color for foam. Alter position to 0.5. Drag both handles closer. It looks more clearly now. This is the simulated Whitewater. Here we can see some cellular foam structures on the surface of the water. The shape of the repellents is disturbed. Basically, we have got the desired effect. As for the render process below, I tested it before and found the rendering time was relatively long with the default material. Well, we can use it if needed, but here I won't use this workflow. I'll set P-scale attribute to these points and then add volume shader to render later, which I'll explain in the material section. Now let's set the P-scale first. There are several ways to do it, like dividing life by age or using the depth attribute. Here we can see the distribution of particles on the surface of the water. In some areas it's dense, while in some areas it's sparse. So I'll deal with it based on point density. We need to apply point cloud. That is, every point searches its surrounding. If the searched points are relatively many, then the current point is in the dense area. Likewise, when a point like this searches its surrounding, the searched points will be definitely few, so it is in the sparse area. Let's type the expression. We need to put the searched points into an array. Define an array first. Input PCFind, the first port. Then add P. Next, the search radius. Lastly, the maximum number of the searched points. Click on this button. Here appear two sliders. Let's see the data here. Display the arrays. Here they are, increase radius and max point. When these two parameters are raised, there appear serial numbers of the searched points in each array. Some arrays have few points, while some have many, based on the current radius and the max count of the searched points. Like this point is in a sparse area, so the searched points are few. Even the max count is just 10, it still cannot find that many. So few points are displayed in the array. But in these dense areas, the number of the search points will be a lot. And the max is 10 as well, since the maximum count in an array is 10. Let's reduce radius. We can see there are only 4 points around point 0, but near point 1, some more points are searched. Next, we need to get the point count in each array. Here we use len. Then apply the result into a variable, that is the count. Let's show the count as well. Now we can see the count of points in each array. The max is 10, the rest is within 10. 1 refers to itself without points surrounding it. That is, those values vary from 1 to 10. Let's fit this range from the minimum to the maximum. The maximum value can be connected with max point. We map it to 0 to 1. Add a ramp to control the map range. Output the result to the p-scale of points. Click this button. To view the effect conveniently, we pick out a small part, like here. To see it directly, we can instance a grid onto those points. Here, we don't need all these attributes, just keep CD attribute. Scale down the grid a bit. In this way, we can see the p-scale in the viewport, thus avoid testing and rendering over and over again when we adjust the p-scale. Currently, the p-scale is larger in the dense areas. We can control the p-scale by adjusting the curve. Besides, these two parameters can be adjusted as well based on our needs. I think the overall p-scale is a bit large. We multiply it by point something. Change the size of the grid back to 1. Reduce the p-scale. I'd like to make the p-scale of the points in the sparse areas smaller. OK. If you want to observe somewhere else, you can also delete it separately. Till now, we have set the p-scale. I'll adjust it further in the rendering section. Currently, I think the underwater bubbles are not enough. If possible, we can resolve the issue rather than resimulate the Whitewater. Otherwise, it will take a long time again. Here we can use the depth attribute. Let's group those underwater bubbles first. Since they are under the surface of the water, the depth is negative. Now the underwater bubbles are selected. Then separate the Whitewater into two parts based on the group. These are the underwater bubbles. We increase the p-scale a bit more. Thus, the bubbles can become way thicker. Another way is to add a point replicate to increase the points count. Lower down points per point a bit here. The bubbles can become thicker as well. Just keep in mind to toggle on copy source attributes. Thus, the added points can inherit the p-scale attribute. Otherwise, it won't have the attribute and some errors may occur. Alright, this is also a feasible approach. You can test which one is better. Here we just use the p-scale. Then we merge it with the rest of Whitewater. This is the final Whitewater. In the next episode, we'll adjust the material and test the rendering. Thank you for watching. In this video, we will talk about material and rendering. Before rendering, we still have something to be done. First, import the mesh. We've added an object merge before, so we only need to replace the path here. Then let's add shaders. For the fluid material, we usually use basic liquid. Then add a uniform volume shader. This shader is to make underwater volume, and the terrain also needs a shader. Let's add a principled shader. Then we simply set the shaders for the objects to be rendered. Here is the final ground. Create a geometry and import the terrain. Change this name. We also need to render the underwater volume, so make a copy of the geometry. This is water, and this is underwater volume. Apply uniform volume to water volume, and basic liquid to water. Then we import the Whitewater. Currently, Houdini seems a little frozen due to the Whitewater displaying. Let's drop a null node, set the display flag to it, then copy the path of the render here, create another geometry. Then paste the Whitewater here. Now let's set HDR. Currently the light source is on the side, and this is in the camera viewport. Show the mesh. The reason I use the side light is that when the waterfall is illuminated, it will look more layering. And the arched shapes, which we mentioned previously, will bring more layers. The light source direction affects light and shadow, so we need to start testing the light direction when we sim flip. As for light intensity, we can test it when rendering. That's it for the settings of the environment. Besides, we need reflected objects. This is a roughly made tree. It started from above, then added a noise, and outputted it to color. Then I deleted some polygons according to the color and replaced the ball. Next, I made some copies and arranged them. At last, I cleared the useless attributes. Then we just use them as the trees here. These holes are the spaces among the leaves. There will be some shadows when the light shines. These trees are pretty rough here. If necessary, you can find more exquisite ones. Then we need to add a shader to the trees. Then the trees will be reflected on the surface of the water. Apply a green color. The saturation doesn't need to be high. Lower the brightness a bit. We can try to simulate the diffuse color of real leaves. The reflection doesn't need to be very high. Reduce reflectivity. Increase roughness a little. Then reduce IOR. It's no need to make the trees reflective too much since they're just reflected objects of the water. Then change the name and apply it to the trees. Also adjust the color of the terrain. Display the material on the object. Set a dark gray color to this terrain. Hide this. Keep the terrain that is to be rendered. Make it darker. Then shift the color of the trees to yellow a little. Lower the brightness. Reduce the reflectivity of the terrain a bit since it's a bit high. Increase the roughness a little. Okay. That's it for the colors of trees and the terrain. We will adjust them in detail in final rendering. Add a mantra at last. Set the render resolution and the output path. Then toggle the commonly used channels. We don't need these channels and just remove them. Then select physically based rendering. Rename it. Now we have finished the preparation work. Next, let's move on to materials and rendering. We'll create the whitewater material and add displacement to the mesh, etc. We have already set the objects to be rendered. To find them easily in the renderer, let's add a prefix for them. Alright, we add the render objects to the renderer. Ground, water, and water volume. Add these three to force objects. We'll get started with them first. Let's adjust the basic material. Disable diffuse. Generally, fluid material doesn't have diffuse property unless we fix some whitewater through vorticity. Then reflect. Specular intensity controls the intensity of the specular component. Reduce it a bit. Jump to reflect objects. Later, when we make the tree reflect on the water, reflection intensity can control the intensity of the tree reflection. Then refract. As seen before, the falling water in the reference is a little light green, so we shift a bit of green to it. That's it for the water shader setting. Then the volume shader. Make it a bit light green as well. If you want a water clearer, cloud density can be lowered a bit, so does shadow density. But if you want a particularly clear water, then it's unnecessary to render volume. The water will come out pretty clear. Okay, we've adjusted the basic shaders. Next, let's move on to the environment. Check it here. Since the environment is a luminous sphere, it can illuminate the scene upward. If we don't check it, the render result will be abnormal. After ticking it, the lower hemisphere will be cut off and it won't illuminate the scene. In this way, the render lighting will be normal. Let's render it. This is the effect including the water, the volume, and the ground. It goes well overall. The falling water is a bit too green because the refraction color is a bit too green. We'll modify it later. Let's see the render time. Currently it's a bit long, almost 4 minutes. Here, I'd like to optimize the render parameters first. It's better to test them earlier. The sooner we optimize them, the shorter the testing time will be. That will improve the efficiency a lot. Let's see the parameters in Mantra. Currently, there is no SSS shader in the scene, so we set SSS quality to 0. This way, ray sampling times can be reduced. We can see the value here, maximum number of indirect samples. The smaller the value is, the faster the render will be. So we can try to lower it if possible. Change 9 here to 2. Now it's lowered a lot here. The render will be way faster. Raise noise level a little bit. Render time will be reduced as well. But there will be a bit more noise in the picture. We keep it as it is for now. Then tile size. I tested it before. Based on my PC's hardware, it's faster when I set it to 32. You can test it on your own and set a proper value. That's it for now. Let's render it again and compare it with the previous one. This is the version after optimization. It has a bit more of noise, but the render time is reduced nearly 4 times. As for noise level, you can set it based on your needs and then tweak these qualities below. Now it's in the test phase. We don't need pretty high sampling times, which will be faster to test the render over and over. That is why we get the optimization done earlier. Okay, keep the current render parameters for now. Let's go ahead. The water is a bit too green. Let's tweak the refraction color. Make it lighter. We'll test it later. Next, we'll set shader for the Whitewater in the sharp network. The Whitewater is particles with p-scale attribute. Houdini renders each particle to a little ball by default, thus it looks stiff. So we need to fill these balls with volume. There is a surface tab here. All the shaders in this tab can work on objects. Here we need to use volume cloud shader to fill up the particles. But it needs an attribute, otherwise it doesn't work. Drop a properties node. Then we add a render property for it. Search it here. There is a uniform volume here. Add it. Then hit accept. Check it here. Then the volume will be evenly filled inside the objects, that is, the density is uniform. Then we need to assign the properties node to the volume cloud so that it can actually work. Now we need to merge these two together and apply them to the particles. Drop a subnetwork. Cut these two nodes and paste them inside. Connect them to the output node. Now the material can work. Rename it. Assign this material to the Whitewater. Then add the Whitewater to the renderer. We render it again. This is the effect with Whitewater. We can see there is some thin Whitewater on the surface of the water, but the density is a bit low now, so we need to increase it. Enter sharp network. There is a parameter on the volume cloud which can increase the density, but it doesn't work well now. Here we need to add one more attribute to control density. On the Render Properties tab, add a volume density. We link it with the cloud density here. Take it up slightly. Let's render it again. This is the effect after increasing the density of the Whitewater. Apparently, it's much thicker than before. I think the Whitewater is a bit dark and not pure enough because there are too many dark areas. We can lower shadow density to brighten it a bit. Also, we can brighten up the environment light. Raise light exposure slightly. This way, the whole scene will be brightened up. In the reference, we can see there is an obvious lightness contrast between the upstream water and the falling water. The current effect also reveals a bit of contrast, but it's not enough. Select Basic Liquid, jump to the Opacity tab, then Maximum Shadow Intensity, lower it a bit, so that when the light source illuminates the water, it will be more transparent. the underwater bubbles will be brighter, which can enhance the lightness contrast between the upstream water and the falling water. Let's render it and take a look. This is the render effect. We can see it's brighter than before, and the white water looks purer. But the current render quality is a bit low, and the noise is a bit too much. We'll raise the sampling times later. Besides, the white water on the surface of the water is a little too much. I'd like to push it into the surface field a bit, thus it can be reduced a bit. You can also make it with your own way, provided that it looks realistic and natural. Let's deal with it. Firstly, import the surface field. Add it here. Solo the white water. To make it into the surface a bit, we need to control the position of these points. Input add P. Also, we need to get a direction. Here we use a function to get the gradient. The first port, that is the surface field. Then 0, which means the sampled surface field. Then add P. Now we get a direction. Suppose this is a surface field. The directions of the gradients are perpendicular to the surface field, so we can get outward directions. We want to make those particles into the surface field a bit. That is, the position equals the original position minus the direction. Then particles will shift into the surface field. As for the offset value, we can multiply by a factor. Alter the value here. We can see all the particles shift into the surface field. We can control the offset position here according to our needs. Okay, let's render it and see how it goes. Besides, as seen before, the render quality is a little low. Let's increase pixel samples a bit, as well as max rate samples. Then render it again. That's it. Compared with the previous one, we can see the white water is shifted a bit into the surface field, and the white water integrates with the water more naturally. Besides, the sample quality is improved this time, so the overall effect is better. Let's take a look at the reflect channel. We can see these highlights are relatively smooth on the surface with few details. Switch to refract channel. We can see these bright color blocks on the lower surface of the water. The edges are quite sharp. Also, the color blocks are quite large with few details. Well, rest attribute can take care of this issue to break up the color blocks. In this case, the water surface will have more details. Now we'll add rest to the mesh. Go inside the matte network. In basic liquid, there is a displacement tab. Check it here. By default, the rest displacement is added based on vorticity. Here are the parameters about it. The first is the scale of the rest displacement. This is the strength of the rest displacement. And then minimum and maximum vorticity. Get inside. The part here controls rest displacement. There is a vorticity attribute which controls where there is rest and where there's no rest. Enter water mesh. We visualize the vorticity color. Connect it. Import the vorticity attribute. Then connect it to color. Drop down a bit to map the values. Now we can see in the high vorticity areas, the color is a bit brighter. Switch to flat standard. Thus, where the vorticity is higher, where the rest displacement is stronger. These two parameters in Fit 1 here actually correspond to these two parameters here in the material. There's no way to visually see the color in matte network, so we can adjust the range in SAP. The rest displacement works only based on vorticity by default, then the range of the rest is somewhat limited. Here I want to add velocity, connect velocity to length, and connect length to color. Then add fit to map the range. The velocity of the falling water is greater, but the vorticity displays pretty dark in the areas of the falling water, which means rest will be hardly added here. So in order to add some rest to this area, I add velocity and vorticity together to get a final range of rest. Well, the range can be controlled by yourself, not just based on vorticity and velocity. You can add some other attributes according to your needs and make adjustments here. Very flexible. Let's modify the source max and the source min. I don't want too much displacement on the surface of the upstream water, so we raise source min a bit here. To displace the falling water stronger, we reduce source max. Reduce source max of the vorticity bit and increase source min. We just add rest displacement in high vorticity areas. Let's add these two and take a look. Because these two partly overlap, when they're added together, there may appear the values greater than 1, then it will be too bright. To avoid this problem, we add one clamp to limit the min value to 0 and the max value to 1. You can tweak this range further. Then output it into an attribute. Break this connection. We give this attribute to basic liquid. Directly replace this one. Now the rest displacement is added based on our setting. Since we have set the range probably in the sub, the fit node is not needed here. Connect it directly to the multiply node. Then wire a trip warp 1 up. We'll render null 1 in the end. Then alter wave scale here. We can adjust it according to the real situation. Raise wave height slightly to make the rest a bit stronger. The following parameters don't work now since we've disconnected them. Alright, let's render it again and take a look. This is the effect after adding rest displacement. Compared with the previous one, obviously the highlights become much softer. Let's see the single channels. Sometimes it's crucial to check issues with single channels. We can see in the reflect layer, some subtle ups and downs appear on the surface of the water, which breaks up large blocks of highlights. And in the refract channel, the edges are quite sharp previously, and the bright blocks are large. But now they're broken after adding the rest displacement. The edges of the color blocks are much noisier, which enriches the details. The range is exactly what we said. We can see the rest displacement in the areas of falling water is much stronger than in the uplands. The displacement in the uplands can be raised slightly. We tweak the range again, connect to color and take a look. To strengthen the rest displacement slightly, we reduce source max of the vorticity and source min. Tweak source max of the velocity. Is fine now. We'll render it later. Till now, we have finished the rest setting. Lastly, we need to add the reflected trees. It's unnecessary to render them since they're very simple. If you have a realistic tree, it's okay to render it. Here, I just want it as a reflected object, so here add it into forced matte. That way, it won't be rendered, but only affects water reflection. And I'd like to make the inner space of the trees larger so that there will be more light shining through it to the surface of the water. You may do it accordingly based on your needs, then render it again. This is the effect with the reflected tree. We can see the reflection brightness of the uplands is reduced a lot, and the bubbles become more prominent. Previously, since both the water and the foam are bright, the overall effect looks messy. But now with the reflected objects, the foam is more noticeable. The effect is better now. You may also tweak it further based on what you want. Now the upstream water and the downstream water display the effect of color contrast. It looks good overall. Alright, I'll render a sequence to check the whole animation. Set the frame range to be consistent with the cache. As for the passes here, you may select what you need for compositing. I don't need them for now. Besides, we increase pixel samples a bit to reduce noise. So much for the materials and the rendering. Then let's start to render it. Thank you for watching. In this video, we will make a simple compositing. This is the render sequence that I've imported. Under the view, I toggled on Gamma Violet. Here I set output space to sRGB. In Fusion, we will grade the color briefly. Actually, the color of the render image is pretty similar to the reference, but it is a little cool. Let's adjust it. Drop a color corrector first. I'd like to make the color of the falling whitewater a little warmer. Let's jump to midtones, since most of the falling whitewater is in midtones. If not sure about it, we can switch to the Ranges tab. Here are the options to check the ranges of 3 tones: shadows, midtones, and highlights. The corresponding areas of these tones will be shown in the view. Result shows the original picture. We can see that the areas we want to adjust are mostly in midtones. Actually, these options are just for checking the corresponding areas. After getting the tone we want, we need to switch back to result. To make the color a little warmer, we can raise red, but not too much. If only raising red, the picture color will be pinkish. Let's add a bit of green. Now the color becomes a bit warm yellowish. Note here, gain in red needs to be higher than that in green. Thus, we can get the yellowish color. Besides, we can lower gain in blue. These brighter areas are controlled by gain. So let's lower it a little. We can see it gets a little warmer. Then I'd like to raise the brightness of this part. Jump to the RGB tab and increase gain. Let's compare the before and after. So now the waterfall is a little warm and shining. The areas of the falling water lack some fog, while it's pretty much fog in the reference. Let's deal with it. Drop a glow. We just want it in the areas of the falling water. So draw a mask. Let's adjust it further. We can refine the effect while maintaining the realism. Reduce a little blend, as well as glow. The edge of the mask is a little hard. Let's soften it a little bit. Adjust the mask here slightly. Compare the before and after. It's a little more foggy and softer than before. This way the contrast of lights and shadows can be also weakened. Let's see what we should do next. There is some spray of the whitewater here. We can draw a simple mask to cover it. Because the spray just appears in the early time period and disappears later, so we can use a later frame to cover the spray. We first need to freeze the sequence. Drop a time stretcher. Hold Ctrl and Shift and double-click on here to delete the keyframes. Let's select a frame without spray in this area. I choose the 100th frame. Set source time here to 100. Then we use this frozen frame to cover the spray. Let's draw a mask. Press Ctrl and T to switch the order of the foreground and the background. So now the spray is covered by the frozen frame. Soften the mask a bit. Then hit the play button and see. There's no spray here. Then connect Merge 1 to Color Corrector 1. Drop a Gamma node. Then link them up. And then connect it to output. Lastly, we can grade the overall color. Increase the saturation. A little is good, not too much. I think it's still a bit cool. Raise gain in red. And a little in green. Compare the effects. It's a little too red, lower gain in red a little. Basically, we graded the color to make the waterfall a bit warmer and added some fog effect. The simulation is good. So I just composited it simply. Alright, that's all for the compositing. Hope it will be helpful to you. Bye!